So this is video 19, continuing where I left off in the last video. We were talking about limits of functions. And here are some examples I'll do in this video. So the first example, you're giving any real number a, and we need to show that the limit as x approaches c of a equals a. And it's pretty simple proof. First, let me recall that for a limit So for the definition of a limit of a function, so you let a be a subset of the reals and c be a cluster point. Of a. And for f, that's going to be a function from a to the reals. We say limit x approaches c of f of x equals L if and only if for all epsilon greater than 0, there exists a delta. So for all x in A, that intersects the punctured neighborhood, which you would say if 0 is less than the absolute value of x minus c less than delta, then f of x, absolute value of that minus L is less than epsilon. Okay, and then this would be like our punctured neighborhood around C, delta neighborhood around C. So punctured delta neighborhood around C. So let's say this is the reals, and we have C, and we have this C plus delta, C minus delta. The puncture neighborhood would be everything in here except taking out C in the middle. All right, and you would say 0 less than the absolute value of x minus c less than delta for all x in that interval. So that's x, and that's the same as saying the delta neighborhood, punctured neighborhood, which should be delta neighborhood around c. Subtract out c. All right, that's what I call it the punctured neighborhood. All right, so that is the definition of a limit, and now we're going to apply this to these problems. So the first example is the constant function. So show this. So in this case, our function f of x is equal to a. So this one's simple because we just pick, so given epsilon greater than 0, we just need to show there exists a delta so that for all x, where x minus c, the absolute value of it, less than delta, implies that you have f of x minus our limit less than epsilon. So let me state that. So wish to show that for all x, let's see, so there exists a delta. So for all x, 0 less than the absolute value of x minus c less than delta implies the absolute value of f of x minus L to be less than epsilon. And then our f of x is a, and then L is a, right? So that's what we need to show. Well, we can pick any positive delta because we know that the absolute value of a minus a, that's going to be 0, which is less than epsilon for any arbitrary epsilon. Okay, so put that in parentheses. All right, so given epsilon, just pick delta to be 1. Then for any x, where x absolute value, so 0 less than the absolute value of x minus c less than 1, we have the absolute value or f of x minus L, which in this case f of x is a, and then L is also a, so a minus a, that's less than epsilon because that's 0. All right, and that's the proof. It's nothing really complicated for that since we have the constant function. So any positive delta would have worked. All right, the next example, we're going to show limit x approaches c of x equals c. And yeah, our function f of x equals x. So we wish to show for all epsilon, there exists a delta. So for all x, such that the 0 less than the absolute value of x minus c less than delta, that implies the absolute value of f of x minus L is less than epsilon. All right, that's what we wish to show. But in this case, our f of x is x, so that's going to be x, and then our L is c, so that's x minus c. So the proof given epsilon, let's just pick delta to be the epsilon. So we have for any x, where we have the zeros less than the absolute value of x minus c is less than delta, then our absolute value of f of x minus L, that's really just x minus c, and that's going to be less than epsilon since that's already less than delta. And that's it for that proof. All right, the next one's a little bit more complicated. So the x squared equals c squared. All right, so this one I'll actually put some scratch work. All right, so I wish to show for all epsilon, there exists a delta. So for all x, where 0 less than the absolute value of x minus c less than delta implies the absolute value of f of x minus L to be less than epsilon. Well, what is f of x? F of x is x squared. And then c, or L, is c squared. So that's going to imply x squared minus c squared less than epsilon. That's what we need to show. Well, we know difference of squares. X squared minus c squared is x minus c times x plus c. All right, and then we could say that's equal to the absolute value of x minus c times the absolute value of x plus c. All right, so that's what we know, and we need this whole thing needs to be less than epsilon. But we know whatever we use for delta, our absolute value of x minus c, that's going to be less than delta for some delta that we pick. So we essentially need to find a way to bound the x plus c. So we need to find a way to bound this. All right, that's what we need to do. And so that doesn't involve this variable x, because x is what we can't have it depend on that. All right, so that's what we need to show. So we need this whole thing, x minus c times x plus c, to be less than epsilon. Well, we know we can make x minus c, the absolute value of that, to be less than some delta. So we need to find a bound for the x plus c. And once we find that bound, then that's going to, then we can pick our delta in such a way that we get the whole thing to be less than epsilon. Okay, so in order to bound absolute value of x plus c, let's try delta being equal to 1. Okay, so if delta is equal to 1, and we know the absolute value of x minus c is less than 1, now note that by corollary to the triangle inequality is that you could have absolute value of x minus c like this less than or equal to the absolute value of x minus c. That's a corollary. So that's absolute value of a minus b like that is less than or equal to absolute value of a minus b. All right, so then what is that going to do? So then we can say the absolute value of x is less than 1 plus the absolute value of c. Okay, because we could add c. So let's see. Since that's the case, since this is less than that, then we could have for absolute value of x plus c to be less than the absolute value of 1 plus the absolute value of c plus c. And that's going to be equal to, well, we could say that's 1 plus 2 times absolute value of c. So we have that the x plus c is going to be less than 1 plus 2 times the absolute value of c. All right, that's our bound. And this was using delta being 1. All right, so to combine all this, so we had x squared minus c squared. That was equal to the absolute value of x plus c times the absolute value of x minus c. Now this is less than 1 plus 2 times absolute value of c. And then times this x minus c, that's less than delta. So this will be this times delta. And we need the whole thing to be less than epsilon. So we need this needs to be epsilon. Well, we can achieve this by letting delta equal to epsilon over 1 plus 2 times the absolute value of c. All right, so then that will give us for here to be equal to 1 plus 2 times absolute value of c times, in this case, our delta being equal to epsilon over 1 plus 2 times absolute value of c. So that way we get epsilon. All right, that's how we're going to choose our delta. And so we have two deltas going on here. We have this is one of our deltas. And the other delta was using 1. So in order to guarantee the limit, we need to pick our delta, let's say call it delta star, to equal the min of 1, and then this delta epsilon over 1 plus 2 absolute value of c. All right, that's what we need to do. All right, just to recap, we need the absolute value of x squared minus c squared to be less than epsilon. By difference of squares, that's x minus c times x plus c. Well, we know we can make x minus c to be less than delta. So then we need a bound for the x plus c. All right, and this bound needs to not involve x. Now it can involve c because c is just some static value. So in order to bound this, note that if we try delta being 1, we know by the corollary to triangle inequality, we could say the absolute value of x minus the absolute value of c, which is less than or equal to the absolute value of x minus c, which is less than 1. By adding c, we get that the absolute value of x is less than 1 plus the absolute value of c. So then we could say the absolute value of x plus c is less than the absolute value of x, less than the absolute value of 1 plus the absolute value of c, because that's going to be less than, or that's greater than the absolute value of x, and then plus c. And let's see, so then absolute value of c plus c, that's, I guess you could say this is technically less than or equal to this, because we would want to do the absolute value of this c, so we have 2 times the absolute value of c. So that makes the whole thing x plus c to be less than 1 plus 2 times the absolute value of c. We could drop the absolute value since 1 plus that, it's going to be positive. All right, and that was the bound that we needed for the x plus c part, and that was using delta being 1. So then we would have this x plus c times x minus c absolute values, and the x plus c is less than 1 plus 2 times the absolute value of c, and then the x minus c is less than delta. And then we manipulate this to be the whole thing less than epsilon by using delta to be equal to epsilon over the 1 plus 2 times absolute value of c. All right, so this is all scratch work. Now the proof. Given epsilon, let's say pick delta, I'll call it delta star, so pick delta star to equal the minimum between 1 and epsilon over 1 plus 2 times absolute value of c. Then for all x, any x where 0 less than the absolute value of x minus c, less than delta star, we have the absolute value of, so our f of x minus L, that's going to be x squared minus c squared, which we said was x plus c times x minus c. And the x plus c, we know that's less than 1 plus 2 times the absolute value of c. All right, and that was for delta being 1. And then this x minus c, that's going to be less than epsilon over 1 plus 2 times absolute value of c. And so that's all equal to epsilon. And that's the proof. All right, so that one was a little bit tricky, definitely more difficult than the other one. All right, so the last example for this video, I'm gonna also do some scratch work. And it's this one. So let me write it over down here. This will be the last example for this video. All right, so the last example, limit x approaches 2, and our function is x cubed minus 4 over x squared plus 1, and it's going to equal 4/5. That's what we need to show. So this one's going to involve a little bit of scratch work. Okay, so we need to show for all epsilon, this delta for all x, where we have the absolute value, in this case, x minus 2 less than delta implies our f of x minus L, where f of x is x cubed minus 4 over x squared plus 1. And then minus 4/5. Need that to be less than epsilon. All right, so that's what we need to show. And then I'll work with the x cubed minus 4 over x squared plus 1 minus 4/5. All right, so what can we say this equals? So using some algebra, combine it into one fraction, where the denominator is going to be 5x squared plus 5 is the common denominator. So we'd multiply x cubed minus 4, multiply that by 5, so that becomes 5x cubed minus 20. And then we multiply x squared plus 1, so we multiply 4 by that. So that's going to be minus 4x squared minus 4. All of that's divided by 5x squared plus 5. All right, that's all as a fraction. So let's see. So that's, what do we have here? So that's just rearrange it. 5x cubed minus 4x squared minus 24 over 5x squared plus 5. Okay, so we want to make use of this somehow. Note that if you plug 2 into the numerator, so note if you do 5 times 2 cubed minus 4 times 2 squared minus 24, that equals 0. So then that means 2 is a root to this polynomial in the numerator. So x minus 2 divides our numerator. Five x cubed minus 4x squared minus 24. All right, so we'll do some long division. I guess synthetic, if you know synthetic. So if we did the long division, dividing x minus 2 into our polynomial in the numerator. All right, so what do we get? So we do 5x cubed divided by x, that's going to be 5x squared. And then we just multiply that by x minus 2, so that'll be 5x cubed minus 5 times 2, 10x squared. Then we subtract all of that stuff above it. That's going to give us a -4 minus -10, so that's going to be 6x squared. And then I'll drop down the minus, technically you could say that's plus 0x, right? So then I would do 6x squared divided by x is 6, so it would be plus 6 x. 6x times x is 6x squared. 6x times -2, that's -12x. Then we subtract all that, and that'll give us 12x. Now I'll drop down the -24. 12x divided by x, that's 12, so it'll be plus 12. All right, so 12 times x is 12x. 12 times 2 is 24. All right, so that's where we get our 0 as the remainder. So when we do our numerator, 5x cubed minus 4x squared minus 24, we could factor it into our factor of x minus 2 times the quotient 5x squared plus 6x plus 12. All right, so that's what it factors into. We using, because 2 is a root, so x minus 2 is a factor. All right, so that makes this. Now that's going to be x minus 2 times 5x squared plus 6x plus 12. All of that divided by 5x squared plus 5. Okay, so now we got a way of involving x minus 2 of the absolute value of it. So this is all equal to x minus 2 times absolute value of that times the other stuff. Okay, then that's 5x squared plus 5. All right, so that's what we had in the beginning. We take this and it turns into this. We know we can make the x minus 2, we know we can make that less than some delta. And that delta is going to somehow involve epsilon. Because we need this entire thing to be less than epsilon. Right, we need this all needs to be less than epsilon. So essentially we're going to have like our delta, this will be less than some delta times, and then I'll call it, let's say m, where m is a bound for this thing. All right, so the question is, how do I find this bound? And we know the previous question, we tried using delta being 1, so that's what I'm going to try. All right, so let's see. So if delta equals 1, Remember that we're dealing with the limit being in a punctured, or yeah, a delta punctured neighborhood. So in this case, this is a delta 1 neighborhood around our x value as x approaches 2. So it'll be the delta 1 neighborhood around 2. So what is that going to be? That's going to be the open interval. So we have 2 minus 1, 2 minus delta, and then 2 plus 1. Right, so we have our real number line. Here's 2. We go sum out delta. This would be 2 plus delta. 2 minus delta. So then our punctured neighborhood, we have delta over 2, subtract out 2 is what that is. And now we're just picking delta to be 1, and that gives us the interval 2 minus 1 and then 2 plus 1. So that's going to be 1 comma 3. So this is our delta neighborhood around 2 using delta being 1. All right, so that's going to be, so now focusing on what we needed to find a bound for, which was the 5x squared plus 6x plus 12 over 5x squared plus 5. All right, so focusing on that, that's what we're going to try to find a bound, and we're going to make use of when delta is 1. All right, so then essentially x is such that 1 is less than x less than 3. All right, so how are we going to do this? And we could have used any delta we wanted. We can make delta as small as we want. It's just for restricting this for some bound, it's probably easiest to try to use delta being 1, which means we have all x in the interval, open interval from 1 to 3. Now, if we focus on the numerator, notice the max of this 5x squared plus 6x plus 12 so the max of that is going to be less than if you were to plug in 3. All right, and that's going to be 75. So for the numerator, as long as, since x is less than 3, then we have 5x squared plus 6x plus 12 to be less than 75. That's for the numerator. Okay, so we want to pick the biggest number we can. So for the denominator, we want the smallest number for our interval from 1 to 3, so for it to be dividing by the numerator by. So for the denominator, we want the minimum of 5x squared plus 5. And that's the minimum of that we want to be greater than if you plugged in the smallest value for x. And for x, we have bigger than 1, right? Because our interval is 1 less than x less than 3. So we want the min to be bigger than if you were to plug in 1 for x, which gives you 10. So for x bigger than 1, then the numerator, or sorry, the denominator 5x squared plus 5 is going to be greater than 10. All right, so that takes care of like our extremes. So we could say 1 over 5x squared plus 5, that's going to be less than 1 over 10, since 5x squared plus 5 is greater than 10. All right, and that's for x bigger than 1. All right, so we have for any x in the open interval 1 to 3, this is using delta equals 1. We have the absolute value of 5x squared plus 6x plus 12 over 5x squared plus 5. That's going to be less than, so the numerator we said that's less than 75. That's the largest it can be. For the maximum is going to be smaller than 75. And then for the denominator, we wanted the smallest for 5x squared plus 5, the minimum of that to be bigger than 10, so that we're not dividing by, we're trying to divide by the smallest number possible. So we have the biggest bound that we can have to encompass this whole thing. All right, so that's our bound. And I was using that for m. All right, so if our bound m, that was 75 over 10, then we would choose delta to be, because we want this whole thing to be less than epsilon, or equal to epsilon. So pick delta to equal 10 over 75 times epsilon. So then we have 10 over 75 times epsilon times 75 over 10. Those fractions cancel out so that you get epsilon. All right, so that's how we're going to choose our delta. All right, so, and the 75 over 10 came from using delta being 1. And then this, it really depends. It could be more than 1, could be smaller than 1. So we want to choose delta star to be the minimum of this one and 1. All right, so that was a good bit of scratch work to get our delta in order to do the proof. Just quick synopsis. So we wrote the f of x minus L part as one fraction, and that one fraction turned into 5x cubed minus 4x squared minus 24 over 5x squared plus 5. We want to be able to utilize the fact that the absolute value of x minus 2 is less than delta. We want to utilize that. Well, we know that if you plug in 2 into the numerator, you get 0. So that means 2 is a root of that polynomial 5x cubed minus 4x squared minus 24. So then we have the factor x minus 2 divides the numerator. So after you do that, it factors in the x minus 2 times 5x squared plus 6x plus 12. So that way we have this x minus 2 that we can utilize. So that's why I wrote it now in the top part in yellow. And then you can break it up. So it's the absolute value of x minus 2 times, and then the absolute value of the other stuff. The x minus 2 is going to be less than delta, and it's going to involve epsilon. and the other stuff is going to be less than some maximum value, some bound or supremum. And so what we did was we found what's the biggest it could be for a value to be, for that to be less than. And the biggest it could be was 75/10, as far as guaranteeing that the absolute value of 5x squared plus 6x plus 12 over 5x squared plus 5 is going to be less than that 75/10. All right, and that came from choosing delta being 1, gave us the open interval 1 to 3. We looked at the endpoints 1 and 3. Now, if you look at the numerator, the biggest the numerator is going to get is going to be some maximum value that's less than 75. That was assuming if you plug 3 in for x. And you want to divide by the smallest number possible so that you have the biggest number for that whole thing to be. So you looked at the smallest number possible that you could divide by. So you wanted to find what's the minimum number for the numerator, for the denominator. And so the 5x squared plus 5, if you chose 1, then the minimum of 5x squared plus 5, it's got to be greater than 10 when you plug 1 in for x. So that way the 1 over 5x squared plus 5 is going to be less than 1/10. So combining that with the fact that the numerator is going to be less than 75, we get 75/10. That's our bound. And that was picking delta to be 1. Again, you can choose delta to be whatever value you want. Delta being 1 is just a common thing that I would use. It just makes it easier. So once I've found that bound, then I can choose the delta for the other thing so that it'll cancel out the 75/10 so that I can get epsilon. All right, so that's all the scratch work. Now the actual proof. And so we don't show all of this in the proof. We just do all this to find the necessary delta in order to do the proof. All right, so the proof. Given epsilon greater than 0, let delta be the minimum of 1 and 10 over 75 times epsilon. So let delta be the minimum of those. So then if 0 less than the absolute value of x minus 2 is less than delta, then we have the absolute value, so our x cubed minus 4 over x squared plus 5, or x squared plus 1 minus 4/5. All right, this is our f of x minus L. So that's going to be equal to, we did some algebra, and we did the algebra. We got it to be such that it turned into the numerator factored into x minus 2 times 5x squared plus 6x plus 12 over 5x squared plus 5. All right, and that involves some algebra. Then we could break this up. So that's equal to the absolute value of x minus 2 times absolute value of 5x squared plus 6x plus 12 over 5x squared plus 5. So we know this is going to be less than, so we had our bound for these, for the 5x squared plus 6x plus 12 over 5x squared plus 5, that bound using delta being 1 was 75/10. And then for the other one, whatever the minimum is, it's going to be 10 over 75 times epsilon. So then that's going to give us epsilon. All right, and that completes the proof. All right, so that's where I'll stop it for this video. And in the next video, we'll prove some limit theorems, like product of limit of functions, as far as taking the product, the quotient, adding and subtracting, and so forth.